Hello, welcome to another Stat 510 video. In this video, we're going to talk about moments and the functions that generate them. Okay, so first we need to define a moment. We define the kth moment of a random variable x to be the expected value of x to the k. So that is assuming it exists given this condition here. But so all that a moment is a particular expectation. And so, for example, the first moment would just be the expected value of x. The second moment would be the expected value of x squared, and so on and so forth. Okay, not particularly interesting in and of itself. Much more interesting is the idea of a moment generating function. We call that the MGF of a random variable x. So this first line here defines the moment generating function. It's a function of t, but it's defined as an expectation. So it is just an expectation that is the expected value of e to the t x, where x is a random variable and t is the input to the moment generating function. Now, why does it have this name moment generating function? Well, because it generates moments. For example, if we take the first derivative and plug in 0, what we end up with is the expected value of x. That is by starting with the moment generating function, taking a derivative, plugging in 0, we generated the first moment. Now, we can generalize this concept. So if we take, instead of one derivative, k derivatives, those derivatives are with respect to t. I don't think I said that, but it's a function of t, so hopefully that was clear. And plug in 0, we get the kth moment. Cool. So that is the definition of a moment generating function, and that is why it gets its name. That is, it generates moments. Take derivatives, plug in 0, you get a moment. So a few quick properties of the moment generating function. If you transform it in a particular way, you can get the new moment generating function. If you add together a bunch of independent random variables, the moment generating function of that new random variable y is equal to the product of the moment generating function of the starting over, I lost my train of thought. That is, I couldn't sequence the words correctly. If you have n independent random variables, x1 through xn, then you define a new random variable that is the sum of those, call it y. The moment generating function of the new random variable y is equal to the product of the moment generating functions of the original xi's. Ooh, that was a mouthful. Okay, so that's going to be really useful. Okay. I pause for a moment. So I'm obligated to tell one of the only statistics jokes that I know, which is that statisticians may be dull, but we have our moments. We'll just move past that. Okay. So why do we care about moment generating functions? Like what use is generating these moments? So there's various uses, and we'll see another one later in the semester when we get into estimation. But for now, one of the most useful things we can do with a moment generating function is use it to check if two random variables have the same distribution. So basically, if two random variables have the same moment generating function with some conditions attached to it, then x is equal to y in distribution. So that means same moment generating functions means same distribution. And just quickly recall, this does not necessarily mean x equals y. It's possible, but not necessary. Okay, so quick example to finish out this quick video on momentary functions. So, classic example here. Let's say we have two random variables, x1 and x2. x1 follows a Poisson distribution with parameter lambda1. x2 follows a Poisson distribution with parameter lambda2. And we also want to say that x1 and x2 are independent. So I'm going to define a new random variable y, which is the sum of x1 and x2. And I ask the question, well, what is the distribution of y? Okay. So there's other ways to do this, but because this is a video about momentary functions, we're going to use momentary functions. So first of all, I could obtain the momentary function for x1 through the use of the definition. But if there's been a theme in this class so far, it's that I am lazy. I don't want to do that. So instead, pull a book off shelf, go to a table in the back of the book. Should really bookmark this. And you probably won't be able to see this because my camera's not very big, but hey, one of the columns on the end here is exactly the momentary function for well-known distributions. Go ahead and unless we ask you to use the definition to derive it, you can go ahead and look it up. Okay, so let's pretend that I did that. And that means that the moment generating function of x1 in this case is e to the lambda 1 times e to the t minus 1. And then similarly for x2, we have e to the lambda 2 times e to the t minus 1. Okay, so now we want the moment generating function for y. So to get that, we will employ this right here. So I can simply, because I'm adding together two independent random variables, I can simply multiply their two momentary functions together. So that's e to the lambda 1, e to the t minus 1, e to the lambda 2, e to the t minus 1. I can do this algebra, so I don't have to be too lazy there. So that's lambda 1 plus lambda 2 times e to the t minus 1. And now I look at this and say, that's familiar. This is the momentary function of a Poisson random variable with parameter lambda 1 plus lambda 2. So then I can conclude, so now I use this here, since the momentary function of y has the same momentary function as the momentary function of a Poisson random variable with parameter lambda 1 plus lambda 2. Thus, we conclude y follows a Poisson distribution with parameter lambda 1 plus lambda 2. Pretty easy. Maybe try to do this an alternative way, maybe using the distribution function, and see how much less fun it is compared to this nice short little derivation here. Okay, so that's it about momentary functions. As always, if you made it to the end of the video, good job, and I will see you in the next one.